you absolutely amazing. You told them beforehand. Okay, I see. It's kind of funny because it's not a very formal lecture, but sure, let's record it. And
If you don't want it, we can just.
I don't really know, but I think it's fine.
As long as you don't say some bad
Exactly
words.
right. What was this other lecture? Rahul's lecture. Was it recorded?
That was not recorded because we just it was from Facebook notification. We didn't realize until like 1 hour before that. That's last minute change.
Okay.
They kind of resist doing it. But if you plan ahead, this time we notified them like 1 day before, or yesterday, so that they realize.
Okay, well, let's get to it because it's 4 o'clock and I'm on a time clock. Okay, so thank you for being here. I think I can hear my voice, right? And this thing is on. Yeah. The thing seems to be on. So thank you for being here. It's an optional lecture. It's a fourth lecture in the day. It's meant just to those who want to learn about CFT. But I see that almost everyone wants to learn about CFT, which is great. Now, obviously, you can talk about conformal field theories forever, but what I would like to do is to kind of continue in some sense where Nikrit stopped, or actually even start a little bit before some of the parts of his lecture, especially his last lecture. And I'd like to develop conformal field theory to a point where we can apply it to construct wave functions of quantum Hall effect and demonstrate relationship between conformal field theory and topological quantum field theories, which we were learning about last week. Now, conformal field theory is a huge subject, and kind of my goal is to try not to assume that anyone knows anything. But on the other hand, there's like no way that I can cover conformal field theory in one lecture, or even in several lectures. It's maybe like a semester-long course. So I'm going to try to talk about it, just to cover things which are important for understanding how how the wave functions in quantum Hall effect should be constructed. So basically, the most important ingredient in conformal field theory, which is used to construct these wave functions, is the concept of conformal block. So my goal is to explain what conformal block is and how to find it in various conformal field theories. But I will need to give quite a bit of background information before I can get to the point where I can define what a conformal block is. But I will not tell you anything beyond what you need to know to understand conformal blocks. Everything else will be omitted. And so because, as I said, there's no way to cover all of this in one lecture, what I'd like to do is to give you as much information as possible just about conformal field theory without ever mentioning quantum Hall effect. And if there is interest, I hope there is, I hope I won't scare you off by this lecture, I'd like to do a second lecture where I actually construct wave functions. One possibility is to do that lecture on Friday, also at 4 p.m. But I'll ask you afterwards if people are interested in hearing this. Well, maybe that would be, after listening to me once, you'll say that's enough, you shouldn't talk anymore. Okay, so let's talk about conformal field theories. Oh, one thing which I need to add before I start talking, I really need to finish at 5:30, and I promise that I'll finish at 5:30 no matter what, because I have to get out of here at 5:30. So if there's any questions, I might even turn around and leave, because basically I'm on the clock. So let's talk about conformal field theories. So conformal field theories are quantum field theories defined in two-dimensional space. So they are defined in Euclidean space-time, but space and time are on equal footing, so such that they're conformally invariant. So generally, such quantum field theories can be thought of as some kind of, or defined by some sort of functional integral, by some sort of imaginary time action, which is an action which is an integral of a local Lagrangian in a space which consists of space and time. But the time is supposed to be imaginary, so space and time are kind of the same thing. This kind of theories can also be recast in the form of partition functions of statistical mechanical models, although usually we think of these as continuum limit of these statistical mechanical models where the lattice spacing has been shrunk to 0. And now conformal field theories are such quantum field theories of that sort which are invariant under conformal transformations. And so first then I need to talk about conformal transformations before I even define what it means for a quantum field theory to be invariant under conformal transformation. And so to talk about this, let's first discuss what conformal transformations are. So conformal transformations are transformations of multidimensional space which preserves angles between vectors. So I will be talking specifically about two-dimensional space. So let's just keep in mind two-dimensional space. But in principle, that can be written in any number of dimensions. So I imagine there is some kind of transformation law that given two-dimensional or multidimensional points in space, they're mapped into some other points in space. And we'd like to do this mapping in such a way that angle between two vectors is preserved. And so that can be defined in principle in the following way, that dx mu dy mu divided by square root of dx alpha dy alpha. So this is equal to dx prime mu dy prime mu divided by dx prime alpha dy prime alpha. So in other words, given two nearby points, distance between which is dx, and two nearby points, I guess with common origin, or maybe some other point nearby the first point with a distance dy, so that you think of this as two vectors emanating from some point. So that's the angle between these vectors, and this is the angle between these vectors after you did this transformation of coordinates. And so you want this angle to be preserved. Now, it's very easy to convince yourself that if you have conformal transformation, and if you define metric, which was flat in the initial coordinates, but maybe becomes a complicated coordinate-dependent object, so the metric should only get multiplied by an arbitrary overall factor. So it's very convenient, actually, even though not necessary, to think in terms of a metric in this case, even though we're not talking about curved space-time in any sense. But if I define a metric g mu nu, which is actually delta mu nu, so chronicle delta in the space of x's, if I do a change of coordinates, so in the new coordinates, I'll get some kind of new metric. And now, if I write down this type of product in terms of the metric, then of course this will be covariant, meaning if I write it in terms of x's, or if I write it in terms of x primes, I'll get the same answer. But as you can see, this does not have any metric. So this actually, after change of coordinates, goes into a new expression which involves metric. And now that metric had better cancel from this expression to give us back this expression, which does not depend on the metric. And the condition for that is that g prime, which I'll compute in terms of these x primes, it should be some kind of function of position, often written as exponential of some other function for some historic reason, times delta mu nu. So as long as the new metric is some sort of overall factor multiplied by delta mu nu, the transformation we're talking about will be conformal. And so that's one convenient method of thinking about what conformal transformations are. So they're the ones which multiply metric if you do change of coordinates by an overall factor, but they don't touch the structure. OK, now what kind of conformal transformations are there? Some conformal transformations are pretty obvious. For example, translations are conformal transformations. X prime mu equals to x mu plus a mu. For an arbitrary vector a mu, this will be conformal transformations, because if you translate stuff, you don't change angles. And there are, in d-dimensional space, there would be d of those. In two-dimensional space, 2 of those, because there are d directions of vector a mu by which you can translate. But then you also have rotations. So, well, OK, I guess I could write down the general formula of rotation, but I don't want to write it. So there are rotations. Let me just say this in words. And in d-dimensional space, there are d times d minus 1 over 2 of those rotations. So then there are, of course, scale transformation. When you rescale every direction by the same factor, these are conformal transformations, because they don't change angles. And notice that scale transformations have to be it is scaling by the same factor in all directions. Because if you rescale by one factor in one direction, by another factor in a different direction, that will change angles, obviously. And so there's only one such scale transformation. And then finally, there is actually a fourth type of conformal transformations, usually called special conformal transformations, for which I'm also not going to write the equation, but there are d of those, actually. And now these conformal transformations exist in arbitrary number of spatial dimensions. But in 2 dimensions, there's actually more. In 2 dimensions, these are just the simplest conformal transformations. And then beyond these, there is also infinite number of other conformal transformations. These are special because, first of all, they exist above 2 dimensions, exist in any number of spatial dimensions. But also, even in 2 dimensions, these play special role because these are the only conformal transformations which map a plane into a plane. All other conformal transformations, as we'll discuss maybe in a second, they map planes into other objects, such as cylinders and other more complicated objects with various properties. So if you want to map a plane into a plane, you have to use one of these 4 transformations. And in 2 dimensions, I'll actually tell you more precisely what these transformations are analytically. I just don't want to write them in d dimensions. And you can always find in the literature how to write them. One thing which I should have told you from the very beginning is that there's this great review by Paul Ginsberg on HepTH from 1991. Basically, like when he started the archive, he put that review onto the archive. It's sat there ever since. So it's very easy to find. And all of this will be given in that review. And actually, almost everything I'll say today, almost everything, is in that review. So it's a useful review to look at. OK, so that would be in d dimensions. But now in 2 dimensions, there's actually, as I said, infinite number of conformal transformations. And that's because actually any analytic function produces a conformal transformation. And so that can be seen in the following way. So in 2 dimensions, it's convenient to use complex coordinates to parameterize points of a 2-dimensional plane if your goal is to use conformal transformations, because complex coordinates like conformal transformations. So imagine I am in 2-dimensional space, maybe parameterized by x and t. And I can set up a combination x plus it and call it z, x minus it and call it z bar. So if I set up these coordinates, I could also discuss metric in z and z bar space. And actually, it's convenient to think in terms of metric, as we'll see. So the distance between 2 points separated by x and t in some space, well, OK, I guess there is a question of what I mean by the distance in a space-time domain. Well, let's think of t as being another spatial coordinate, just denoted by a funny letter. So they have space dimension x and space dimension t. So that I don't go into the detail of what it means to have time, which acts like space. But so then the distance would be x squared plus t squared, which is obviously z bar. And so it's convenient then to think of complex space as just being like change of variables from xt variables to z bar variables. And it's also convenient to define a metric with respect to which all the scalar products can be computed. So it's clear from this formula that if the original metric was identity matrix, this metric is actually not an identity matrix. Rather, it's a matrix which looks like 0, 1 half, 1 half, 0, such that z bar is equal to g mu nu, z mu, z nu, where I define z mu as a kind of like a vector which consists of z and z bar. And so it's often convenient to use this metric tensor when you contract indices in the complex space. And so obviously there's also inverse metric, which is 0, 2, 2, 0. And now let's see. If I do a change of variables, and let's actually, in anticipation of what I'm about to say, let's do a change of variables given by an analytic function. So suppose z is some function of z prime. So that's a change of variables from coordinate z to coordinate z prime. And correspondingly, I have z bar, which is complex conjugate function, which is a function of z prime bar. I don't know, z bar is complex conjugate z, but I denoted the conjugation of the function itself by a star. But I think you know what I mean. So let's say I have this kind of change of variables. Then the new metric, g, so the only non-zero component of the metric is the off-diagonal component, ZZ bar. So the, let's see what I wrote here. So the new metric is given by the component of the old metric multiplied by df dz prime, df star, dz bar prime. And so that's the off-diagonal element is the only element which we should be interested in, because these elements are all 0. And this is the usual law of changing coordinates for the metric as a 2x2 tensor, having lower indices. I hope you guys are familiar with this. And so you see that, so what happens to the metric? Basically, the metric gets multiplied by some factor, which is a product actually of two functions. One depends on z, one depends on z bar. And that's exactly the condition for conformal transformations, that the metric got multiplied by an overall factor. So clearly, these transformations are conformal. But also, in math and theory of functions of complex variables, it's actually proven that this type of transformations are conformal. So in principle, we should all know that these are conformal transformations, and these are actually the only conformal transformations. OK, so the message here is that in 2 dimensions, any analytic function gives us a conformal transformation of 2-dimensional plane. And now a good idea is to then classify them according to this type of analysis, and then to see what we have beyond this type of analysis. And so to do this kind of classification, it's actually convenient to look at infinitesimal conformal transformations. So imagine a situation where, OK, let me change what I mean by f. So here, z is a function of z prime, but let me also imagine that z prime is a function of z. And let me imagine a situation when z prime is very close to z. So we do a transformation of coordinates, with new coordinates are just small perturbation of the old coordinates. And so this could be written as z prime being z plus some function of z. Now, of course, this has to be an analytic function, but it's an analytic function which is z plus something very small. Now, it's a good question what it means for this to be small, but anyway, let's not worry about that much. Something which can be somehow shrunk to 0. And so that would be the example of infinitesimally small conformal transformation. Conformal because it's analytic, but it's also very close to z prime equal to z. And now epsilon of z can be Taylor expanded in Taylor series with the coefficients. Let's call them alpha n, z to the n. Let's imagine all of these coefficients are infinitesimally small. And so then we generate, by choosing different terms in this Taylor expansion, we generate different conformal transformations. And so the simplest of them is epsilon being a constant, where only the zeroth term is retained. So z plus alpha naught. So alpha naught is some complex number. So these are actually translations. And there are 2 of them because alpha naught is a complex number. So it has 2 parameters in it. So these are analogs of that translation, which I wrote more generally over there. So then we can imagine z prime being equal to z plus alpha 1 multiplied by z. So that would be the first term from there. So this is actually both translations and rotations, depending on whether alpha is chosen to be real. Sorry, not translations, scale transformations or rotations. If alpha 1 is real, then that's like rescaling. Z gets multiplied by 1 plus alpha 1. So we rescale z. So that's rescaling, scale transformations. And if alpha 1 is purely imaginary, you can convince yourself that this is an infinitesimal form of a rotation. A rotation would be multiplying z by e to the I phi. If phi is infinitesimally small, you expand it, you get this, with alpha 1 being purely imaginary. OK, so these are scale transformations and rotations. Then there's a third law, z prime equals to z plus alpha 2 z square. And so this law actually gives us those special conformal transformations, which I didn't list here, which also exist in high number of dimensions. Now, all further transformations corresponding to taking z cubed, z fourth, and so on. So these are the transformations which don't have analogs in high dimensional space. And now, these 3 transformations are the ones which map a plane into a plane. Now, that's not entirely obvious from these formulas, because these are infinitesimal formulas. But let me just say in words, I'm not going to derive this. Deriving that, by the way, is a good exercise, actually, but it does take a little bit of time. So you could repeat these infinitesimal transformations infinite number of times to generate finite transformations. And so this, of course, when it goes into a finite transformation, just becomes translated by a finite amount. This becomes either scale transformation or rotation by a finite amount if you repeat this many times. And this actually becomes a more complicated rational function of the form z prime is equal to az plus b divided by cz plus d. Or rather, that kind of rational function encodes all three of these transformations, because it actually depends, if you think about it, on kind of three parameters. Well, there are four coefficients, a plus bz divided by c plus dz, but then you can cancel out one of them, right? And so you kind of generate all three of these transformations. And so this type of transformations map a plane into a plane. All other transformations generate for us functions which are more complicated functions, such as square root of z, for example. Square root of z obviously maps a plane into a half plane, so that's not really a plane into a plane. Or exponentials of z map things into cylinders, and which are periodic in z, and so on. So these are the only global transformations, and they play a special role because they don't change the plane. Yes? Yes, so let me actually write this. So if you apply all of these transformations in a large number of times, you'll generate finite transformations. And those will be of the form z prime equals to, I'm just thinking, should I cancel out some coefficient? No, I'm not going to cancel this. az plus b, cz plus d. So this really depends on three parameters, because you can cancel one of them, divide by one of them, right? And if you make those coefficients small and Taylor expand, you'll generate one of these three, depending on which parameters you choose. Furthermore, this is the kind of transformation, it has group property. If you repeat it twice, you go back to that same transformation, only with different parameters. So that means it is the kind of the most general transformation of this sort, whose infinitesimal form has this form. Okay, so all other infinitesimal transformations will give us more complicated functions, as I said, which don't map a plane into a plane. And so that becomes important in further applications of conformal field theory. Okay, so these guys, they have a kind of a similar form. By the way, I'm saying this, just want to make sure that I'm telling you the right thing. No, I think this is the right thing. This is the right form of them. They involve various scalar products instead of, and it's also a ratio of scalar products because you're dealing with vectors in d dimensions. Something like that. Like, I don't remember off the top of my head, but Ginsberg gives it in his review, so you can look it up. As a matter of principle, there were certain formulas which I decided not to look up beforehand, so that I wouldn't be tempted to start writing them and then spend a lot of time discussing them when we will not need them. So I didn't look up these transformations in d dimensions, but analogous formula exists in d dimensions. Okay, so now that we've listed these transformations, we can ask what it means for a quantum field theory to be invariant under conformal transformations. So it turns out that there is a theorem demonstrated, I guess, back in 1960s, that if you have a quantum field theory which is invariant under translations, but translations kind of obvious thing, rotations also kind of common thing in quantum field theories, but also under scale transformations, then such a quantum field theory is necessarily also invariant under conformal transformations. By that I mean by transformation 3. So in other words, for a quantum field theory, invariance under 1 and 2 necessarily leads us to invariance under 3. And that's actually also true in any number of dimensions. So the first 3 of these, which got projected into the first 2 over there, imply the fourth one. And so the argument for that went in the following way. So, and by the way, to show this, I'll have to rely on certain facts from quantum field theory, which I do not plan to derive. You'll have to believe me, or hopefully you've seen them before, although they're not always emphasized in quantum field theory courses. So imagine that I have a theory which is invariant under infinitesimal transformation x mu prime is equal to x mu plus epsilon mu of x, which is kind of like what I wrote here, except this was specifically in complex coordinates. This is more general in some coordinates. Could even be in d-dimensional space. So imagine that there is a quantum field theory invariant under these. So then such a quantum field theory will have a conserved current. And so this current can be written in the form J mu is equal to T mu nu. Let's write it with an index downstairs. T mu nu epsilon nu, where T mu nu is the stress energy tensor or energy momentum tensor of this quantum field theory. So that is a fact of quantum field theory, which may or may not be emphasized. And so from here, it actually follows that a theory which is scale invariant is also conformally invariant. And to check that, we just need to go through a few steps. So first of all, what does it mean that a theory is invariant under translations? So translations imply that epsilon nu is equal to a nu. It's a constant. And then the fact that the current is conserved implies that T mu, d mu, T mu nu times a constant, which I won't write. Well, no, I guess I'll write it. Is equal to 0. And that means, since this is arbitrary constants, infinitesimally constants actually, that means that stress energy tensor is conserved. But we know all of this. This is how we define stress energy tensor. But more interesting, what happens if a theory is invariant under scale transformations? By the way, the fact that it's invariant under rotation means that T mu nu is symmetric. T mu nu is equal to T nu mu. That can also be checked if you check rotations. So I guess rotations would be T mu nu is equal to T nu mu. Let me not check that. You have to think about what epsilon mu is for rotations to see that. But the third point would be that if we choose epsilon nu to be x nu times some coefficient lambda, and that means we have a scale transformation. So then conservation of J mu for scale transformations would imply that d mu applied to T mu nu x nu had better be 0. And now that's because the current is conserved, and the current has to be this, and epsilon nu is this. I just plugged it in and didn't write lambda, which is just an overall coefficient. So T mu nu should be conserved because the theory is translationally invariant. So when d mu hits T mu nu, that's 0. When d mu hits x nu, that gives us Kronecker delta. Kronecker delta means that this quantity is really T mu mu trace of stress energy tensor. And so we see that that stress has to be equal to 0. And so a scale invariant theory must be must have stress energy tensor which is traceless. So that's the condition for the theory to be scale invariant. And then the final step is, it turns out that if a theory has stress energy tensor whose trace vanishes, such a theory is also conformally invariant. And that's because for more general conformal transformations, d mu J mu would imply what? It would be, again, d mu, T mu nu, epsilon nu, where epsilon nu is some general function, but such that it defines conformal transformations. And so there is a term when d mu hits T mu nu, but that's 0. And there is a term when d mu hits epsilon nu. And so that would be this kind of term. But T mu nu is symmetric, and so this can be rewritten as T mu nu, d mu epsilon nu plus d nu epsilon mu. And now for conformal transformations, you can actually argue that the thing which is written here is proportional to Kronecker delta. And that's because if you think about it, this quantity is actually precisely the change in the metric under coordinate transformations. So that, I guess I would have to write down how metric changes under coordinate transformations and consider infinitesimal coordinate transformations and just check that this will be how metric changes. Metric g mu nu goes into g mu nu plus this. And since metric should only get multiplied by overall factor, that means whatever gets added to the metric has to be proportional to delta mu nu. This means this is proportional to delta mu nu for any conformal transformation. As long as it's conformal, this has to be true. And well, yes, but then we'll have to discuss. So that's true, actually. So you can think of f as being z plus epsilon of z. do this derivative, we'll get 1 plus epsilon prime here and 1 plus epsilon bar prime. Then you have to think about that is the same as what's written over there. Well, okay. Anyway, you should know how metric transforms, so you will know this formula. In fact, often when people study general relativity and how metrics transform, they actually discuss this. That's infinitesimal law of changing of the metric. So that's proportional delta mu for conformal transformations, as well as for scale transformations. And so this is 0 for any conformal transformation. And so this means that a theory which is scale invariant is conformal invariant. And that's really exciting because we have a large variety of scale invariant theories. Any quantum field theory which is at a critical point is a scale invariant. And that means it's also conformal invariant. And so that was recognized in the 1960s by Polyakov, who then immediately demonstrated that there are certain consequences of these conformal invariants in any number of dimensions, which would be valid for critical points of interacting systems. And that was done just as an elimination group was being invented. Yes? Does not? No, it does. Definitely, because that whole thing is based on this idea. No, I think for local scale invariant quantum field theory, it would also be conformally invariant, I'm pretty sure. Well, okay, yes, you have to say some additional words. That's true. To tell you the truth, I actually don't know where unitarity would come in, because what comes in is this. And this is locality. So you need to have local theory. There are theories which are not local, which are scale invariant and not conformally invariant. I don't know of any theories which are scale invariant, not conformally invariant, and local, even those who are non-unitary. And people do study non-unitary conformal field theories all the time. Although you could say maybe they're designed to be conformally invariant, right? They're not just scale invariant. Okay, but I personally don't know of any examples of non-unitary local scale invariant but not conformally invariant theories. In any case, here we're only interested in unitary theories. Although, by the way, there's still a debate whether non-unitary theories are useful for quantum Hall physics or not. The consensus is unitary theories are safe. Let's use unitary theories. But every once in a while, there are ideas in the literature that maybe non-unitary theories are also useful. Okay, but in any case, you see that there is this line of arguments. And I think there is no doubt in literature, at least for reasonable quantum field theories, whenever they're at a critical point, which is scale invariant, that point will also be conformal invariant.
I missed the point. So, like in 3, you already proved that your scale invariant T is traceless.
Right. But if T is traceless, the theory, then the current which corresponds to conformal transformations, more general than scale transformations, that current is also conserved automatically. Because stress energy tensor is traceless, because this is delta mu nu, so this would be T mu mu, so this is 0. So here we've proven that if the theory is scale invariant, stress energy tensor is traceless. Here we've proven that if stress energy tensor is traceless, the theory is invariant under all conformal transformations, including scale transformations, but also all the rest of them, whichever you can find. Okay.
So the claim is when you have 1, 2, 3 automatic.
Yes. 4 follows from 1, 2, and 3. So invariance under translations, rotations, and scale transformations imply invariance under conformal transformations. I think this is general statement of Noether's theorem. So if there is some sort of coordinate transformation which happens to be the symmetry, so your action is invariant under this transformation, then this will be conserved. And that can be shown generally. Of course, important, the action is invariant, not covariant. You can always write down covariant actions, which always the same in any coordinate system. But I'm writing here an action without metric. I change coordinates, and the action happens to look exactly the same in new coordinates. So if that happens, then this will be the conserved current. Okay, so now we're in the position to start discussing consequences of conformal invariance for quantum field theories. So in quantum field theory, usually we like to compute correlation functions of some objects. Could be spins of the Ising model or some fields whose correlation functions we'd like to compute. And so I imagine that we have some objects which we'll refer to as operators, because maybe they're operators in the quantized version of quantum field theory. Some people just say maybe it's just a language, convenient language of calling these objects operators. And so these operators will have correlation functions. For example, some operator A, which sits at the position Z1. So it depends on Z1, Z1 bar. B at the position Z2, Z2 bar, and so on. And this correlation function will have some sort of expression, who knows what it is, in terms of the functional integral, which I will not write down. It'll be different for different theories. But so this type of expressions, and maybe I should, for completeness, divide this by this. And so that defines some sort of correlation functions. And we'd like to be able to compute these correlation functions. Well, we will not be computing them, but we would like to understand the consequence of conformal invariance on these correlation functions. So it turns out that conformal invariance places restrictions on these correlation functions, which are especially severe in 2 dimensions. And so to be able to place those restrictions, we need to apply conformal transformation to this type of correlation function and discuss how it changes and also demand that it's invariant under these conformal transformations. And so here comes one important point. So it's only the invariance under these conformal transformations can be implied. So in other words, when we do these conformal transformations, correlation functions are invariant. If we do conformal transformations which go beyond these, they don't map a plane into a plane. And so that correlation function will not be invariant. It'll be just mapped into another correlation function in a different geometry, like half plane or cylinder or whatever other geometry we map, whatever Riemannian surface we get out of the analytic function which we use for our conformal transformation. But these transformations are convenient because plane goes into a plane, and that means in new coordinates the correlation function should look exactly the same as it looked in the old coordinates if we have conformal invariance. And so in order to be able to impose this condition that new correlation function is the same as old, we need to know how these objects change, or how the correlation functions change under conformal transformations. And so usually a concept of primary field at that point is defined, of primary operator, and it's defined almost like out of the blue, but then subsequently it's justified by subsequent developments. The primary field is defined as a kind of a generalization of a tensor. So if we had some kind of a tensor-like object whose correlation function we're computing, we know exactly how it changes under coordinate change, because tensors transform in a particular way. Now, we imagine an object which looks like a tensor, but kind of a generalized version of the tensor, which transforms according to the following rule. A of z, z bar, is equal to a new object in new coordinates, z prime, z bar prime, multiplied by dz prime, dz to the power of h, and dz prime bar, dz bar to the power of h bar. Now, if you look at this formula, this looks just like a transformation law of a tensor, such as t mu nu or g mu nu, except for a tensor, we would have just one such ratio per index of the tensor. So, well, depending on how many of them you have. But here, this is raised to the power of h. So it's not really tensor. It's some kind of weird tensor with fractional or even arbitrary number of indices, which doesn't have to be integer. So let me not try to justify it any further, because I'll spend too much time on justification, and you can justify it later as you continue developing the theory. Let's imagine that we have objects which transform according to this rule, and see what consequences this rule gives us. So h and h bar are called dimensions of this field A, conformal dimension actually. And h doesn't have to be equal to h bar, although in many cases it is equal, but in some other cases it's not equal. We'll see in a second why h is natural to call dimension. This actually coincides with what we usually call dimensions in the normalization group sense of critical theories. Yes? What about them? Yes, they're real numbers, right? You could, in principle, take them complex, but if you try to do that, you will not get unitary theories. So they will be real numbers. OK, so that's the transformation law, which is postulated at this stage. Now, to be able to take advantage of this law, we need to write down its infinitesimal form. By the way, so an operator which transforms according to this law, and not every operator transforms according to this law, it's called primary operator of field. And that's a very important concept. We'll see that all fields in conformal field theory can be divided into primary fields and those which follow from primary fields, which usually called descendant fields. So if we know all primaries, descendants can usually be fixed by conformal invariance. So it's important to know primary fields. And now primary fields, when you have them, well, we can now find their correlation functions, actually. The correlation functions are severely constrained by conformal invariance. And to do that, let's consider infinitesimal conformal transformation. Z prime is equal to z plus epsilon of z. Let's plug it in here, and let's expand this in powers of epsilon, and just equate the lowest order term in powers of epsilon on the left and right-hand side. And so when we equate, obviously, here we have a z z bar. Here we have a prime of, as we expand, we'll get a prime of z z bar also, because we'll be plugging this in here and expanding. And so we will call a minus a prime at the same point z z bar as the change in the operator as we go from one reference frame to another, or as we do conformal transformations. So delta a is defined as a z z bar minus a prime of z z bar. And then from this formula, we can show that this is equal to, let's see, epsilon dA plus epsilon prime times h times a. Let's for a second imagine that only z is being changed, and let's not touch z bar. So imagine that epsilon is this, but epsilon bar somehow is 0, even though we're used to thinking of bars being precisely complex conjugates of non-bars. But sometimes it's convenient just to separate them. So, if there is some epsilon bar, it'll just get added to this. It will be epsilon bar d bar plus epsilon prime ha. By the way, I'm going to be using these notations where d is d dz. Epsilon prime is really d epsilon. I don't know. I could use either notation, but sometimes it's, well, I don't know. Maybe I should be more consistent and write this as d epsilon times h times a. So because epsilon and epsilon bar enter linearly, we can consider them independently, and we don't have to simultaneously change z bar by epsilon bar. And if we do, there will be an additive contribution. It looks exactly like this, but epsilon bar, d bar epsilon bar, and h bar here. Everything else stays the same. So let's just look at the holomorphic part of conformal transformations without worrying about anti-holomorphic part. Then this is the change in this operator. I hope everybody can see that if you plug this in here and expand in powers of epsilon, that's what you get in the lowest order term. OK, so that gives us the transformation law of these operators. And this allows us to actually impose restrictions on correlation functions of various operators. For example, let's consider the correlation of a z bar with some other field b w bar. And let's call it g of z bar w bar. Now, I will only impose conditions on these correlation functions having to do with holomorphic conformal transformations. And so I will be able to actually kind of forget for a while how it depends on z bar, w bar, because we'll be getting conditions having to do with z and w at first. And that's one of the advantages, or one of the common things which happen in conformal field theory. We can worry about holomorphic sector separately from the anti-holomorphic sector, and then think about them together later on. And so what I mean by this specifically is, well, let's impose the condition that this correlation function is translationally invariant. Actually, we should know what it means for the correlation function to be translational invariant. It means it only depends on the distance between these 2 points. But let's try to do it formally using this technique. So we choose epsilon to be constant. If epsilon is constant, the change in the field is constant times dA. And then we calculate the change in G under this transformation. And that's like change in A plus change in B. But change in A is simply epsilon times dA. This is 0 because epsilon is constant. And so we generate then the following rule, which says dz apply it to G plus dW, apply it to G had better be equal to 0, and that's the invariance of the correlation function. If I do my translations, correlation function should stay the same, and that means applying that change to A and to B, I should get 0. And so it follows from here that G depends on Z minus W, which of course we should all know that that's the consequence of translations. Now let's look at consequence of scale transformations and actually simultaneously rotations. So in that case, we will choose epsilon to be proportional to Z times some constant, which I don't really care what it is. And so delta G, what is it equal to? Well, I have to change A and change B according to this rule, but now epsilon is Z or W. And so what I'm going to get then is that Z dZg plus HA times d epsilon, which is 1, G plus W dWg plus HB G. This had better be equal to 0. But of course, G is a function of Z minus W, so that we should already take into account. So if you plug this into this equation, you will see there's only one solution of that equation, that G goes as some constant divided by Z minus W to the power of HA plus HB. So here I assume that A and B have different dimensions, HA and HB. So that's the consequence of scale invariance. And that should be kind of clear. So look, that means that this correlation function is scale invariant. If I rescale my coordinates, it gets multiplied by the scaling factor to this power, and that's why it's called dimensions, because that's how things transform under scale transformations. That's exactly what we mean by dimensions in the sense of renormalization group, for example. But now we also have conformal transformations where epsilon is proportional to Z squared. And we can apply that rule again. And that rule tells us that Z squared dz G plus 2ZHA G plus W squared dWg plus 2WHB G equals to 0. And now here, of course, we have to plug in this form now with an arbitrary constant. And so that's possible to do, and I don't want to do the algebra, but the outcome of this algebra will be that if HA is not equal to HB, then this correlation function must be 0. If HA is equal to HB, this correlation function is just this. It doesn't impose any further constraints. This satisfies this equation. So it follows from here that G is 0 unless HA is equal to HB. So it follows from here that two objects, which are this kind of primary fields, cannot have non-zero correlation unless they have the same dimension, which typically means unless it's basically the same field. So the two different primary fields don't want to have correlation, which is non-zero among themselves. And so this was first observed by Polyakov in late 60s, because to show that you only need conformal transformations valid in any number of dimensions. So this is actually in principle true in arbitrary number of dimensions. That two-point correlation function is only non-zero if HA is equal to HB. And actually back then, most people said, who cares? So two-point correlation function are non-zero only if dimensions are the same. So what? Nothing profound follows from it. And it's only maybe 15 years later that two-dimensional conformal field theory came into place, where this became important. Okay, so we derived how correlation function looks, but by the way, that only gives us the holomorphic part of the correlation function. Of course, once you do the same thing in the anti-holomorphic part, you'll find that G also has the same form with bars for dimensions in the anti-holomorphic part. And overall G then must look like some constant divided by Z minus W to the power of HA, well, actually twice HA, because HA must be equal to HB, times Z bar minus W bar twice H bar A. And we don't need to repeat this for the anti-holomorphic sector, because the argument is exactly the same and gives us something which is multiplicative in holomorphic and anti-holomorphic sector. Show that this would work for both holomorphic and anti-holomorphic sector independently if I apply this to this function. Okay, so conformal invariance allows us to fix the form of the correlation functions, but actually already scale invariance almost fixed it. The only thing which conformal invariance demanded is that dimensions are the same of the two objects whose correlation functions we compute. But now more interesting things start happening if you start examining higher correlation functions. And it turns out that for all practical applications, including quantum Hall effect, it's important to go up to the 4-point correlation function. And then you can stop once you're at the 4-point function. You don't need to go beyond. You could, but you don't learn a lot more. So you could look at the correlation function of 3 objects. And let me only write the holomorphic part of that. So there will be this correlation function is also a product of holomorphic and anti-holomorphic parts. Yes.
Question. So when you do a full gas correlator, charges have to go down to 0.
Mm-hmm.
But if you do it, it looks like opposite. Well, I know the
But these dimensions are the same. So what matters is that dimensions are the same.
Right. So I just said it's a square of the chart. But what I'm
Right.
wondering is, if there's something not dimension, but not
Yes. You would need to look also at the invariance under U1 transformations, which you can also do in the conformal language. Or you don't even have to use conformal language. You know what that means. That charges should add up to 0.
what is it? Does it correspond to some?
Yes, so it would mean that the charges should add up to 0. There will be something, it will be like a separate transformation generated by the U1 current. And these are transformations which are actually generated by stress energy tensor. I haven't discussed that yet, but right. It's not implied directly by this, right? Because it's something extra. It's this U1 symmetry which those theories tend to have, which gives you extra conditions. But it's all compatible with what I said here, which is generally true. Okay, so 3-point function. So how does it behave? Well, you know from scale transformations that it should, if you rescale all coordinates, it should get rescaled by the sum of the dimensions of these objects. And it does. But conformal transformation actually fixes it even further. It fixes it in the following way. It has z1 minus z2 times ha plus hb minus hc times z2 minus z3 times hb plus hc minus ha times z1 minus z3 times ha plus hc minus hb. And so this particular assignment of powers between these 3 is due to conformal transformations. So if you only do scaling transformation, you'll discover this function should have this form generally with these 3 powers adding up to the sum of h's. But you don't know what these powers are. You only know what the sum is from the point of view of scale transformations. But conformal transformation actually gives you what these powers are. And that means conformal transformations fix 3-point function completely. Like there's no freedom of any sort left up to the overall coefficient c. Just like in the 2-point function, there was also an overall coefficient c. Okay, so 3-point functions you know fully. What about 4-point functions? And so 4-point functions are more interesting. So their conformal transformations, don't fix them up completely. And let me write down how they fix them specifically for, so I don't want to write the most general formula for all 4 different operators. And let me write it for the case when, let's say, I have just 2 operators, A and B, at 4 points. And so you can show by repeating the same arguments, but now with 4 points, that this correlation function has to go as 1 divided by z1 minus z3 to the power of 2ha, z2 minus z4 to the power of 2hb, multiplied by some function of x, where x is a very special ratio, z1 minus z2 times z3 minus z4 divided by z1 minus z3 times z2 minus z4. Sometimes it's called anharmonic ratio. And this f of x is arbitrary. It cannot be determined by conformal transformations only. So the conformal transformations fix this prefactor, but they leave this function arbitrary. And so this is the function which is called conformal block. And this is the one which eventually becomes important for quantum Hall. But right now we know very little about what they are and where they come from. So this will come up later in more detail about what these conformal blocks are. But so just by conformal invariance, well, of this sort, it's not possible to tell what this f of x is. It's just some function of x. Any function would satisfy all these transformations, translations, rotations, scale transformations, and conformal transformations.
So how do we know s must be that kind of
X, it's,
f of x?
I mean, you basically you take this function and you plug it into these three equations, except these are equations written for 2-point functions, depending on two coordinates, z and w. These guys have 4 coordinates. So there will be a more complicated equation, which involves, first of all, sums of all derivatives with respect to z1, z2, z3, and z4. That would be the first condition. That will be the same thing as here, except it will be a sum over all 4 coordinates and 4 fields. And finally, there will be this guy. Also, it will be twice as long as here, because there will be 4 points involved, z1, z2, z3, z4. And then you just have to work out what the solution of these equations is. And it turns out the solution looks like this, where f of x is undetermined. Doesn't matter what f of x is. It always satisfies this. Essentially, because f of x always satisfies these equations with all h's being 0. It's kind of like solution of uniform version of that equation. Anyway, you can think about this. So f of x is designed in such a way that if you set h to 0, no matter, well, all of these equations give you precisely 0. And this part is designed to take care of h parts in these equations. Oh, but those are no longer global conformal transformations, so they don't give me constraints. They map my correlation function onto functions in other manifolds, not planes, and they change. In fact, those more complicated conformal transformations are used to map correlation functions on the plane onto correlation functions in other geometries. A common example, we have quantum field theory at finite temperature. It lives on a strip with periodic boundary conditions, for example. We map it onto a plane. We know correlation functions on the plane, and we map them back onto the strip. And that's how, in conformal field theory, you can compute these correlation functions. And we map them using the transformation law for arbitrary z prime and z could be related by any function. OK, so now let me add one more piece of information. So this only concerns the holomorphic sector. In reality, even you have some statistical model, these objects will depend not only on z's, but also on z bars. And so it's possible then to compute the correlation function of these combined objects in the following way as 1 over, let me use the notation z13, which is a shorthand for z1 minus z3. So z13, 2ha, z24, 2hb, z13 bar, 2ha bar, z24 to the power of 2hb bar, and then that gets multiplied by a sum. So usually, as we discover, there are many different conformal blocks which correspond to the same correlation function. And generally, you have to take some kind of combination of these. Fi of x times fj star of x bar, let's say. And so that's the form of the general correlation function, which depends not just on some complex coordinates, but depends on actual positions in 2 dimensions, where the position is denoted by z and z bar. And notice that this correlation function, it will satisfy all these constraints, which only act on holomorphic part, because each term in the sum will satisfy this constraint. And the sum of this kind will also satisfy this constraint, independently for holomorphic equations of that sort and anti-holomorphic equations of that sort. And so that's why we can combine them like this, because they'll satisfy these equations. But we can't do anything more complicated. Like we cannot maybe take f and raise it to the power of a star or something, because that will not satisfy these equations. Only products will satisfy these equations, will not talk to each other. OK. It's only because if all 4 fields are different, this prefactor becomes more complicated, and I don't remember off the top of my head how it looks like. When this dimension is the same as this, and this dimension is the same as this, then it's easier to remember, you know. And you mean dimensions? Well, okay, these correlation functions often are singular when 2 points approach each other. So like, for example, here, what does it mean to compute 2-point function at the same point? And that's common in these theories, right? Basically because there is some cutoff. You can't approach them closer than cutoff. So you have to be careful with how you approach coordinates to each other. Okay, so we actually, at this point, learned everything which follows from conformal invariance without doing anything more sophisticated and going into details of 2-dimensional conformal field theories. So far, everything which I said could actually be done in any number of dimensions. But in 2 dimensions, there are further simplifications. Well, they have something to do with the existence of these extra symmetries, but they also have something to do with just the structure of 2-dimensional theory being more sophisticated. Well, let's see. Maybe I'll just write here. And so the very important aspect of conformal field theories is the role of stress-energy tensor in a 2-dimensional conformal field theory. So let's see. Stress-energy tensor, in general, it's a matrix. In conformal field theory, in 2-dimensional conformal field theory, it's a 2-by-2 matrix, and its trace is equal to 0. So T mu nu delta mu nu is equal to 0. Now let's go from Cartesian coordinates into the complex coordinates. So if we go into the complex coordinates, then mu nu goes over z and z bar, and this becomes a metric tensor in z bar notations. And remember, it's an off-diagonal metric tensor. It has 1/2 in the off-diagonal entries, or maybe actually 2, because if this guy has upper indices. And so if I want to write down the condition for the energy momentum tensor in complex coordinates to be traceless, that condition is written as tzz bar is equal to 0. Because the trace of energy momentum tensor is really tzz bar plus tz bar z, but t is symmetric, so literally it's just tzz bar is equal to 0. So it's a pretty powerful condition. Just one matrix element or one entry of the matrix corresponding to the stress energy tensor is 0 as a consequence of stress energy tensor being traceless. And so in complex coordinates, then stress energy tensor only has 2 components. It has component tzz and component tz bar z bar. And furthermore, the conservation of stress energy tensor implies that d bar tzz is equal to 0. And that's because, again, for the same reason, what is the conservation of stress energy tensor? It's d bar tzz plus d tz bar z, because the metric is off diagonal. You have a question?
Yeah. I didn't understand. How does trace this test that the off-diagonal?
Because so in complex coordinates, this becomes tzz bar equals to 0, because this becomes the metric, and the metric only has off-diagonal elements. Remember, it's like 0, 0, 2 to 0, 0, 1/2, 1/2, 0, depending on whether indices are above or upstairs or downstairs. And so it becomes tzz bar plus tz bar z, and it's symmetric, so it's just tzz bar. It's equal to 0. Okay, but then there is even more powerful consequence that this has to be true just by equations of motion, and for the same reason of g being off diagonal. But this is already 0, as we agreed. And that means tzz is holomorphic, only depends on z. It does not depend on z bar. And
the same condition as what you got from scale, not scale from road.
yeah, this is also true.
Translation.
Yes, this is from translations. This is from scale transformations. But I'm using them at the same time, just maybe in the opposite order, because it's easier to argue like this. And so it follows from here that tzz depends only on z, and it's usually denoted by t in conformal field theory, just an object which depends on z only. And t bar depends only on z bar. It's usually denoted t bar, and it's tz bar z bar, which depends only on z bar, again by the analogous equation. If you take the second index to be z bar, you'll get the second equation that tz bar, z bar, depends only on z bar. And so in conformal field theory, there are basically two objects, t of z and t bar of z bar, with which we can work. Now, we can now use stress energy tensor to generate conformal transformations. So what I mean by this is the following. So we know that in quantum field theory, we can define charges which correspond, well, these are conserved quantities, which correspond to symmetries. And these charges, their commutator with various objects, give us the change in this object under the symmetry transformation, which gives us this charge. This is part of Noether's theorem. And now we actually know how these primary fields transform under conformal transformation. They transform according to this law written here. But on the other hand, we can write down this conformal transformation as a commutator of the charge, which corresponds to the conformal transformation, and this field. And now, what kind of charge corresponds to conformal transformation? So usually, the charge is defined as an integral over space of the time component of a conserved current. Now, in conformal field theory, it's very convenient to think of space as, see if I have a two-dimensional space. I think of space as moving in the radial direction. So this is my space. Actually, I take my words back. That was what Ari told us earlier. That was his space. But I'd like to have this to be time. And I'd like this to be space. So my space is the angle of rotation, and my time is the radial direction. And so this is usually called radial quantization, when I consider my time going in the outward direction. Now, what Ari considered was, it's something called angular quantization, where angle was his time and radial direction was his space. And so if I define my space as living, on circles, on concentric circles whose radius is time, then the conserved charge, which corresponds to the conformal transformation, will be defined as an integral over a contour, which is that circle over there, over the variable z of epsilon of z, t of z. Now, it takes a little bit of algebra, which I don't want to do, of taking j mu from the Noether theorem, which I had before, and working it out. What happens if you take this j and integrate it over space? You have to take time component of j, which is outward j, and integrate it in the space direction. Then you'll discover that you'll end up with this formula. This is only for the holomorphic part. There is also a contribution of the t bar, which goes as dz bar, epsilon of z bar, t bar of epsilon. I said epsilon, z. But epsilon is whatever conformal transformation I'm looking at. Remember that the conserved current looks like this, right? So basically what I have to do is I have to rewrite this in complex coordinates. I have to choose j to look in the outward direction, in the time direction, and I need to integrate over space. And then I need to write this as an integral over complex coordinates. And this is what I'll get in the holomorphic sector. There will be a corresponding expression in the anti-holomorphic sector. So that's how we chose our space. It becomes compact. So in principle, we can, in this type of theories, we can define space as being anything you want. Historically, it had to do with this being some kind of model of string theory. And strings, they kind of have compact direction and then dimension, and they move somewhere, I think. But subsequently, people realized that it's really a matter of choice, and it's a very convenient choice to think of this direction as space and this direction as time. OK, but so this q is a conserved charge. Conserved means it takes the same value no matter how big my circle is, no matter what my time is. dq dr, r is the radius of this circle, is conserved. And so one condition which we can then derive is that the commutator of q with my field A, so it had better be equal to epsilon dA plus h d epsilon A. And so from here, we'll immediately derive powerful constraints on stress energy tensor and how it behaves in the vicinity of field A. Now here A is implied to depend on some position. Epsilon also depends on this position. All of these derivatives are with respect to that position. just as I thought, we're slowly running out of time, and I definitely won't be able to even explain how to compute conformal blocks. So the second lecture is still needed if anybody would like to learn how to compute these blocks and apply them to quantum Hall effect. But we're slowly covering the basics. I mean, if you ever decide to learn conformal field theory, you will have to go through all of this. This is like the minimum amount you need to know to understand conformal field theories. Let's think about what it means to compute a commutator of Q with A. It had better be equal time commutator, which means Q and A live at the same time. That means the radius of the circle over which I'm integrating this has to be equal to the radius at which the field A is located. So to compute this commutator, I take A at a point W, and I act on it by Q, integrate it over epsilon of z, T of z. Let's write it here. So I'd like this to be at the same time, but I also like T to sit on the left from Q. And remember, all correlation functions in quantum field theories are supposed to be time ordered, which in this language means whichever has bigger absolute value of coordinate sits on the left, whichever has smaller value of coordinate sits on the right. So we'll choose this to be a circle such that absolute value of z is equal to absolute value of w plus infinitesimal amount. Well, I already used up epsilon for infinitesimal amount. Let's say plus 0. I think you'll probably understand what I mean, right? So I'm integrating this over a circle which is just tiny bit larger, well, has tiny bit larger radius, where, by the way, this is not Q, this is A. I raised A and I wrote Q. OK, and so this is by definition Q times A. And if I'd like to write down A times Q, I would need to subtract from it integral over z, epsilon of z, T of z, A of w. But here I'll choose absolute value of z equal to absolute value of w minus 0. It's a slightly smaller circle over which I'm integrating. Now, and that means actually that these guys are time ordered, you know, and they're changed. It's really A times t, but that's implied in this formula. And now look, so I have an integral over one contour which goes outside w, and over another contour which goes inside this w, and that's the contour z. And this can be deformed into a single contour which just goes around w. So this is, I guess, what I just said is one of the most powerful statements which people who invented conformal field theory invoked. They basically invented this trick. Everyone else follows from this trick. Like if you understand this trick, you understand everything else, which there is in conformal field theory. And so this amounts to then integrating z over a tiny circle around w. So z is w plus, I don't know, rho e to the I phi. Well, I hope you know what I mean. So you take your z over a small circle which surrounds w of epsilon of z, T of z, A of w. So that's what it means to compute commutator. It means to integrate that thing around w. But on the other hand, we know the result which should come out from this integration. And that means we actually know how this thing behaves when z approaches w. It's very easy to convince yourself that the only way to match this formula is to demand that T of z, A of w goes as HA, I guess that's HA, times A divided by z minus w squared plus A prime of w divided by z minus w plus other terms which are not singular when z approaches w. And then by the usual theorem of complex analysis, if you plug this expansion in here, you can actually do this integral. It'll produce for you precisely these two terms. So this will produce for you this term, and this will produce for you this term. And so saying that operator A changes according to this rule is completely equivalent to saying that when stress energy tensor approaches A, it has, as we say, operator product expansion. So these two fields sitting nearby can be thought of as some series of which the first two singular terms we know. And what we don't know is the rest of the terms. But the first two are known. OK. And so that gives us something very important. That's the first example of operator product expansion. And so the entire conformal field theory is constructed on a clever application of these operator product expansions over and over again in different contexts. And so that's how primary fields behave under operator product expansion. So now this operator product expansion, it tells us that it might be a good idea to do the following trick or operation. Let's take T of z and Taylor expand it in powers of z. Actually, not even Taylor expand, Laurent expand, because T can blow up when it approaches different points. Let's Laurent expand it. In general, there will be some sort of series which goes from minus infinity to plus infinity. And usually the coefficients of this series are written as minus n minus 2. The reason for that being that T has scaling dimension of 2. And that in this way, Ln have scaling dimensions of n. So it's convenient to define it in this way with the shift of 2. And now look, by analyzing how T of z behaves in the vicinity of A of 0, by applying this formula with W being 0, we see right away that first of all ln's acting on A, if n is greater than 0, all such ln's must be 0. Because if they were not 0, there would have been terms which would have been more singular than z minus w squared. There would have been terms z minus w cubed, fourth power, and so on. But there are no such terms, so all such ln's give us 0. And then L naught acting on A actually multiplies A by its dimension. And all L minus n for positive n acting on A give us something which is not 0. Now, it turns out that these ln's, they are operators which form an algebra called Virasoro algebra. And I think there's still time to discuss Virasoro algebra in a second, which these ln's form. And so ln's behave in some sense like spin generators of SU2 transformations, which are generators of angular momentum or spin. So when you have SU2 generators, we have generators S plus, S minus, and S0. And when we construct representations such as spin 1/2 or higher spins, first we discuss states on which raising operators give us 0. S plus is 0 when acting on it. S0 when acting on it gives us spin. And then S minus lowers the spin and gives us other entries in this representation or other terms or other components, I guess. Now, this is sort of analogous that Ln with n greater than 0 play the role of raising operators, except there's infinite number of them for all n's. L0 plays the role of Sz in the SU2 algebra, and L minus n plays the role of lowering operator. And you can see that A then behaves kind of like the spin which points up, right? Cannot be raised anymore, but could be lowered, and is characterized by some number. And so it turns out that this A, by virtue of being primary field, and this follows from this, and that in turn follows from that primary field formula on the opposite blackboard. So by virtue of being primary field, A is, as people say, is the highest weight representation, or the simplest representation you can construct of that Virasoro algebra, which ln's form, which I haven't showed yet. So all other representations will be the ones for which ln acting on them are not 0, and all other fields are those other representations. The primary fields are these kind of highest weight representations, which are annihilated by ln's greater than 0. And that's one of the ways of justifying the concept of primary fields later on after introducing them, because they are actually they're representations of the Virasoro algebra of the highest weight type, and all other representations can be constructed from them by applying L minus n's. Now, I haven't proven that, and I don't plan to prove it, but hopefully I'll have some examples of how this works.
Is there a sense of
Convergence. Well, okay, it's a Taylor series, and it's all in the realm of functions of complex variables. So usually those series have some radius of convergence. Now, of course, you can imagine a series with coefficients which blow up as a function of n very rapidly, and then they will have radius of convergence of 0. That usually does not happen in good conformal field theories. In other words, all correlation functions are nice finite functions which you can Taylor all around expand with expansions which have finite radius of convergence, which is usually equal to the distance to the nearest other fields in these correlation functions. So they are convergent, I would say, with some radius of convergence.
So the convergence also depends on if I put
Yes, right. Because those other terms actually, I mean, well, those other terms, you can't define them in terms of A only. They're kind of this type of terms, actually. And exactly what they do depends on what other operators are in this correlation function. And actually, we will need to know that later on. But I will run out of time to talk about this today. OK, so we've established this operator product expansion. We've established that these ln's act on the field A in the following form. Notice, by the way, that so these are coefficients of expansions of t around 0. And so they act on A in a simple way if A itself is at 0. If A sits at W, we could define ln of W. Where we'll write here z minus W. It also makes sense to think about ln's defined at 0 in the vicinity of A defined at W. And that becomes a little bit more complicated, but also sometimes useful. So that maybe I'll discuss that later on. OK, so the next thing to discuss is actually to understand this Virasoro algebra and where it comes from. And so it comes from how stress energy tensor itself transforms under conformal transformations. Now, stress energy tensor is part of tensors, has indices t mu nu. And remember that this primary field transformation law was inspired by transformation law of tensors. And actually, tensors with two indices would transform according to that law with h being 2. Actually, tzz would have h2, and tz bar z bar would have h bar being 2. And so that tells us that we should write down the following transformation law of the stress energy tensor. It's the same as there, except h is 2. That's the only difference. So we'll write epsilon of z t prime, or I guess dt, well, the same thing, of z plus 2 epsilon prime of z times t of z. So that would be the law if t was just a primary field of dimension 2. Now, it turns out that this is not all there is to it. There is one more term, and that term is not easy to understand. And so I would like not to derive it, although I could, in principle, I could derive it. And that term is equal to epsilon triple derivative of z multiplied by the coefficient proportional to a number called central charge, which I'm sure everybody heard about in one context or another, which I think divided by 24. Although I actually have not checked this coefficient this morning when I was writing this down. So you could see if you could check whether that's 24 or not. So that has to do with conformal anomaly. The fact that stress energy tensor behaves in a funny way if the theory is in a curved space. So there's a way to relate this to conformal anomaly. But that would take me another 20 minutes. So I don't want to do that. Let me just declare this is true. And let me also observe that doesn't contradict simple scaling. So stress energy tensor has dimension 2. And look, each derivative adds increased dimension by 1. So this has something of dimension 2 plus derivative. This also has something of dimension 2 plus derivative. But this has triple derivative, which is the same thing as having something of dimension 2 and derivative. So at least all powers match. And now, look, if we have this law, it also follows from here that if I consider this type of an integral, but with a being t, so this is epsilon of z t of w, I had better, as a result of that integration, get this right-hand side written here. And now it takes a little bit of algebra to understand what's the analog of this for this formula, if this guy is t and the result is that thing. And so the result then becomes t of z, t of w, as z approaches w, behaves as c divided by 2 divided by z minus w to the 4th power plus 2t of w divided by z minus w squared plus t prime of w divided by z minus w plus and terms which are regular. You can take this, plug it in here, do this integral by residues, as we always do. And in particular, this guy had better give you this term. And yes, well, OK. You could try and see whether you'll get C over 24 or not. Hopefully, you will. Do you think it's C over 12? OK. I don't know what it is. Maybe it's 12. Let's write 12. It just doesn't look right to me. Remember that you have factors of 4 and 3 from differentiation, but you also have factorials which you have to worry about, and you also a factor of 2. Okay, I don't want to do this because we only have 5 minutes left. And that's a simple algebra to check whether plugging this into that integral and doing it by residues give you this, and with what coefficient. Maybe it is 12. Okay, and so it follows from here in particular that L naught acting on t is 2t. L minus 1 acting on t is t prime. And actually the same thing happens here with A. L minus 1 acting on A is a derivative. In fact, L minus 1 always produces derivatives when it acts on things, not even primary fields. But also from here it follows that L2 acting on t is c over 2 from here. And that means that t is not a primary field. It's actually a descendant field, descendant of the identity. You can show that t is L minus 2 acting on identity with a little bit of work. And so finally, now with this amount of knowledge, you can use these equations to compute the commutator between Ln and Lm. And that's computed by realizing that Ln can be thought of as contour integral t of z to the power of n plus 1. And Lm can be thought of as contour integral over w of t of w to the power of n plus 1. Because if you plug in this Laurent expansion, precisely gives you 1 over z and 1 over w, which picks for you Ln and Lm. But to do the commutator, what you have to do is you have to choose here a contour which is a circle, and z is a circle which is outside the circle for w, a larger circle, in one term. And you have to subtract from it another term when z is the inner circle inside w, which is the same as saying that z is being integrated over w. So here, z goes around w, and then later w will go around some contour, going around the origin. And so you need to do such double integral, and you plug in this expansion for t of z, t of w, and you do these integrals by residues. And if you do them, you will arrive at the following formula. You will get n minus m times ln plus m plus c over 12 n squared minus n delta n plus m comma 0. And again, this 12, like I'm not guaranteeing for you that that's true. You just have to check, plug in. So when you plug this for these OPE, this term for this operator product expansion, and do the integral over z over w by residues, and then integral over w around the origin by residues, and you had better get something like this. So the coefficient I will not guarantee for you because I haven't checked it.
So this is all understood inside the calculation. These are all
Well, so these are understood as either you think of this as operators, some kind of operators in the quantized version of quantum field theory, or this is understood as being part of some correlation function.
right. So in the formal sense, why do you put TA instead of AT then?
CA, where?
In the second minus, no,
Here?
previous one, yeah.
Just because I said it's all time ordered anyway.
So you just
So
think of it
as long as this is fulfilled, that means this is AT.
Right.
Because all products are understood as time ordered. We don't work with any other products. Because it's understood as some sort of functional integral, which can only produce time ordered correlation functions. Okay, so I think it's a good point for me to stop. Let me just tell you now what I can do with this. So now that I have these operator product expansions, I can actually calculate any correlation functions which involve stress energy tensor. So given correlation functions without stress energy tensor, I can calculate the ones with it by using this expansion, this one and this one, and certain facts from theory of functions of complex variables. That's the power of two-dimensional conformal field theory. So once I'm able to compute correlation functions with arbitrary insertions of this t, I will be able to compute correlation functions not only of primary fields, but also of descendants, because descendants are obtained by applying L's to A, which means by fusing stress energy tensor with A. But I know how to fuse T with A within any correlation function. It in principle follows from this formula. So it's possible to derive this. And so then once I do that, I'll be able to argue that all fields in conformal field theory contain primary fields and descendants are tied to primary fields. Descendants are results of acting by L minus n or by powers of L minus n on A. And so whenever I compute operator product expansion of two primary fields, on the right-hand side, I will get primary fields and I'll get descendants. But descendants will always come together with primary fields, and in fact will be completely fixed. So if you know that some primary field appears in the operator product expansion, you also know precisely how descendants of that field appear in this expansion. It'll be possible to show by using these equations. And so if you specify which primary fields appear in the operator product expansion of two primary fields, you know everything about the entire operator product expansion, because you know how all other fields, descendants, also appear in that expansion. So specifying which primary fields appear as a result of operator product expansion is literally equivalent to the fusion rules of topological quantum field theories, which we were studying last week. So fusion rules is all about fusing two primaries and getting a primary. In fact, the term fusion rule, to the best of my knowledge, appeared in the context of conformal field theory to specify how we get primaries in the operator product expansion, because all other fields are tied to primaries. Once you know which primaries you get, you know which other fields you get as well. So we'll understand this, and finally we will understand how those fusion rules affect the choice of conformal blocks. We'll discover that every 4-point function has as many conformal blocks as there are primaries appearing in the operator product expansion of these. And so we'll be able to label the few conformal blocks by number of primaries which appear in the operator product expansion of two primary fields. So once we understand this, we'll basically be done as far as learning how conformal field theory works. Of course, we should also discuss how to compute those blocks in various cases. But once we do that, all which will be left for us will be to argue that those conformal blocks in many cases can be understood as wave functions appearing in the context of quantum Hall effect. That was contribution of Reed and Moore. And then finally, how we can now start extracting these blocks from different conformal field theories and interpreting them as wave functions and producing the whole zoo of different potential wave functions for all sorts of exciting quantum Hall states. Some abelian and some non-abelian. But I think it's a good time to stop now. So if you guys are interested, I could continue. Yeah, so I could continue on Friday, but now I really have to go.